Hello, everybody. So there are definitely going to be some typos in this. The first is that this eruption wasn't in 2020, it was in 2019. So we'll kick off with that. I've started strong. Now you know what to expect with the rest of the presentation. I've got loads of different co-authors on this presentation, and I'm presenting the work of a lot of different people, including collaborators around the world and in Tonga as well. And we've been given really useful access to Tongan data through the Tongan Geological Services and Survey. So I'd like to acknowledge them too. So there's the correct date. The August 2019 eruption of Volcano 0403-091, or Volcano F as it's also known, basically went completely unnoticed. These are all figures I've stolen from Philip Randall's paper because he's done a good paper on it and I didn't want to make them myself. But this eruption, it occurred underwater from a volcano nobody cares about, somewhere near Tonga, and we would never have known it had even happened if it hadn't produced a pumice raft. So quite often we get underwater eruptions that we're not aware of. They happen all the time, and this area's got additionally poor seismic coverage. It's hard to hear things acoustically because of the shape of the seafloor, so the hydrophones far away don't really pick up activity, or it's hard to position it. And so quite often we don't know about these eruptions at all, unless they produce something that we later sort of run into with a boat, which is what happened here. So the eruption happened, but we didn't know about it until 2 days later, when some yachts suddenly sailed into a big raft of floating rock, which was a surprise for them. And so what we did, they contacted some scientists, and it eventually ended up on Twitter, and that's how I found out about it. But we were able to trace back, sort of based on where we knew the prevailing winds and currents were, and where the pumice raft was at this point. We could trace back where it come from. And looking at satellite data, and this sort of picture in the middle labelled B, this is the only evidence in the satellite data of any eruption in the area, and it sits right on top of this unknown volcano. This is a caldera volcano. There are lots of calderas in the Tafua Arc. Hunga Tonga Hunga Hapai was one, still is one. This is another one. It actually looks quite similar, and the patterns of eruptions between the two are quite similar too. But this was a much smaller eruption. So we traced it back. We found this sort of steaming ring in the satellite data, and we're like, right, got it. Bit of discoloration, but no evidence of the eruption at all. So without the pumice raft, we'd probably never even have picked up on this. This volcano is erupting low K, so low potassium dacite. This eruption was the same, geochemically almost indistinguishable from the last eruption, which was in 2001, or at least the last eruption that we know about. There may have been others. And pretty much all of the eruptions from this volcano itself have occurred on the caldera rim. And that's quite typical for caldera sort of volcanoes in the Tafua Arc. They tend to have quite a lot, quite regular small eruptions from vents that sit on the rim of the caldera. But then occasionally, like Mike showed earlier, they go a bit bigger. So this is sort of the pathway of the pumice raft, initially when it was picked up on the 8th of August, and then sort of day by day when it was visible in satellite data. It was not huge. There was a much bigger one in 2012, which got a lot more press. This was like not a huge pumice raft, but it was big enough, and it caused quite a lot of disruption. So it washed up in Fiji about 3 weeks after the eruption, and then on further Fijian islands another 3 weeks later, and then eventually in Australia about 6 months after the eruption. So we got a NERC agency grant to go and look at this because it was quite well constrained and it had produced a pumice raft, which is interesting. But obviously you don't get very much money, which is always a disappointment. So we went out and we used quite small rubbish equipment. We had a fishing boat, and we had like a little blue ROV. So it's a sort of a robot with a camera on the front, and we hammered a bit of wood on the front to use as a scoop, and then we just drove it into the seafloor. That was one of our sampling strategies. The other thing we did was we had really good, actually, very well engineered, like little mini grab. That was very helpful. And we also had sort of because we didn't know what the seafloor depths were here, and we knew the summit of this volcano was quite shallow. For safety, we also had basically a surfboard with a single beam echo sounder on it that we ran ahead of the boat so we didn't slam into the seafloor. But it all went actually very well. So we did 7 days of fieldwork altogether, 6 here, and very conveniently, right after we got the funding for this, another volcano just to the south of this one erupted as well. So we also went and did that for a day as well, which isn't bad going for 65 grand, I think. So this is what the seafloor looks like. So we wanted to have a little look at at which vent had been active. There's a series of 3 vents on the northern edge of this caldera. The 2001 eruption happened from sort of the middlemost that you can see here, and potentially the one that's also to the left of it. So sort of those 2 most westerly vents. There we are, that's the way to describe it. This eruption produced a new vent. I'll show you that in a minute. But we didn't know that. So in order to pin down where the eruption had actually happened from, we looked at things like clast sizes, and then also things like alteration, where we saw biofilms on the seafloor and where we saw that the biology had been wiped out, basically. So that's what's shown on these pictures. The top 2 show clast sizes, so the median and the maximum clast sizes, and their distribution across the area that we surveyed. And then the bottom one with the yellow and blue dots on it. So where we see the blue stuff, we've got biofilms. So that's where we've probably got some kind of, phones off, please. That's where we've got some kind of potentially like fluid flow coming out of the seafloor. And we saw lots of patches of orange staining as well. So we didn't really see much active fluid flow, but evidence that there definitely had been some. And then we saw colonising organisms, so sessile organisms, things like sponges and corals, where the brown dots are. So those areas weren't really affected. These are just some pictures of the seafloor, taken with our beautiful ROV. We had good data from before the eruption. So the German vessel had been out, I think it was Sonne, went out and did some surveying right before this eruption, 2015 or 16. And then we resurveyed the summit area and we differenced those. And we found that the new vent is sort of where this black circle was. And the 2001 eruption vent is where the grey circle was. So that vent sort of got filled up and we created a new one just slightly to the west of it. So these vents seem to be migrating west. We also saw quite a lot of material deposited on the seafloor, again, mostly to the west of the vent, and that's the prevailing wind direction and also the prevailing current direction, so that makes sense. Some pictures of changes in the seafloor there. What we were really interested in, though, was the pumice that had produced this floating raft and also the stuff that had sunk. And a lot of this data is quite preliminary, so there was a bit of sort of arm waving to come. We've started doing XRCT work on the pumice, and again, this is one of the things about urgency grants is they run out, so then you've got all this great data and you have nothing to work it out with. So we're doing this sort of as and when we get the time to. It's really hard to do XRCT of pumice. Anybody who's tried to do it will know, because you get these big vesicles with very, very, very fine glassy sort of films between them that are really hard to resolve, even in very, very high resolution scans. So we've been doing a lot of scanning. We're doing some more in February, and we've been using, there's some reconstruction tools in Aviso that you can use to kind of put the films back in, but they don't work that well. So we've also done some helium picanometry, and I'll show you that as well. But we started looking at bubble populations, so bubble size populations, and what we see is we've got quite a lot of bubbles that are quite big and quite a lot of bubbles that are very, very small and not a lot in between. So we seem to have these 2 different sort of generations of bubble formation, which are probably to do with the ascent. This is a picture of the raft that washed up on one of the islands. So the top picture is the island before it got hit by the pumice raft, and then the bottom picture is it inundated by pumice. So all of that grey around it isn't cloud, that's rock. Here are some more lovely XRCT images of pumice. We also see some evidence in, these are all floating samples. So at the moment we've only scanned the stuff that floats, not the stuff that sank. That's the next bit of this project we're doing in February. But definitely in the floating samples, we see differences in density. So we're probably seeing some kind of mixing of different compositions potentially in those samples as well. So that's quite interesting. We were really interested in the difference between pumice that was floating and pumice that was sinking. And this work is ongoing. Now, initially, we thought that was going to be just density. And actually, measuring the density of these things is a real pain as well, because they're full of bubbles. They don't really have sort of an outside surface. So you end up like wrapping them in parafilm and measuring their weights in water and air and all sorts. We tried 2 different methods for measuring density. We didn't really see a major density difference between the stuff that was floating and the stuff that was sinking. So you'd naturally expect the stuff that sank to be noticeably denser. That's not the case. On average, very, very slightly denser, but we have, say, denser clasts that floated than some of the ones that we find that sunk. So density doesn't seem to be the controlling factor here. We looked at chemistry. The blue dots on these diagrams are the floating pumice, and then the other colours are all stuff that was on the seafloor, so different grab samples. Slight differences, maybe the stuff that sank is a little bit more fractionated, but also we tend to see slightly more microlites in the sunken pumices as well, which you can see in those two pictures. So the top picture has all those little microlites in, that stuff that's on the seafloor, and then the image beneath it doesn't have them, and that's stuff that floated. But what worked really well is looking at the connectivity thresholds for this stuff. So we sampled pumice at 3 different locations. So we sampled it at the volcano itself. And we were given samples from the raft when it was first intersected by a yacht. So we have sort of like time 0. And then we also collected it on 2 different islands. So the one it hit at 3 weeks and the one it hit at 6 weeks. So the stuff that sank is the blue dots. And then the stuff that floated for at least 3 weeks is sort of the beige. And the stuff that floated for 6 weeks is the red dots. As you can see, there's not much difference in porosity for any of those. So the porosity between those samples, apart from one outlier, which is just there to make me look bad, but the porosity on the whole doesn't seem to be particularly different between floating and sinking pumices. But when we did helium peakonometry, we found that the connectivity in the stuff that was floating was much lower. So there's some work done by Samuel Mitchell looking at floating pumice from the Harbour eruption, which is the 2012 one. And he found this separation too, that for certain densities of pumice and certain porosities, if you have enough connectivity, it will basically waterlog very, very quickly and sink. And if you have lower connectivities, then it takes much, much longer for water to ingress into all of those different pore spaces, and you tend to get floating. The other thing that I think is quite interesting here is that separation between the stuff that floated for 3 weeks and the stuff that floated for 6 weeks. Now, obviously, there's only a few samples. We've got absolutely loads of pumice, like bags of it. So there will be more dots to go on this. But at the moment, it also seems like the stuff that's floating for the longest is also furthest away. So it's the least, it's got the sort of lowest connectivity within those bubbles. So that's another key finding. So in terms of floating versus sinking, it doesn't seem to be one controlling factor at the moment. It seems to be there may be some geochemical differences, there may be some slight density differences, and there's also differences in things like the pore connectivity or the bubble connectivity within it that are preventing water from getting into it and waterlogging it. So lots of things that we are still investigating. I also just wanted to touch on the impact of pumice rafts and also volcanism in the Pacific Islands, the South Pacific in general, because these pumice rafts washed up on quite isolated islands, and the people in those places really, really rely on like small vessels to get to school, to get to hospital, to fish, to get anywhere really. And they're quite isolated, small communities. This island, so Lakemba, has 1 flight in and out a week. And we have done actually some work there, interviewing community leaders, talking to them about what the impacts of the raft were. There were some really interesting things that came out of it. It did have a financial impact. So because people couldn't fish and because they couldn't get fuel in and out of the island because it blocked the harbour, basically the whole island had to shut down for 3 weeks until it washed out again. The other thing that was interesting is that there was a warning issued over VHF radios for vessels in the area to avoid the pumice raft. But these communities don't use VHF, they use mobile phones, and there was no warning issued through a way that was accessible to them. So actually, the pumice raft washing up on Lakemba came as quite a surprise. So they weren't really prepared for it. And, you know, in the Asawa Islands, which are further along, they had to carry their boats across the island over to the other side to launch them. And then the final thing that was really interesting was it had a quite profound impact on the wildlife. It killed a whole bunch of turtles. So what we think is happening there is that they are getting caught underneath pumice, and then when the tide comes in, they're drowning basically because they can't surface. So there's also sort of quite a few implications for things like turtle nesting grounds and stuff as well, which in Fiji are quite important. So yeah, that's all I've got to say really. Lots of things still happening, but happy to try and answer any questions. Thanks.